warn you all guys, I just adopted a little dog and she's still very anxious. So I might have to jump up and calm her down. Sorry, sorry.
Yeah,
like
no
right
problem.
now she's sitting here with me. I don't know if you can see her, but yeah. Okay, thanks for the introduction and thanks for inviting me to this workshop. I'm super excited to tell you about some of our recent research on at the intersection of robotics and vision. Let me start by kind of, let me tell you my high-level vision. When I think about robots, I think about all of these little different tasks a robot is supposed to do. For example, cleaning the house, cooking, repairing things. And we humans are amazing at acquiring all of these different skills, but also being able to apply this to really any environment that we're put in. I mean, we adapt fairly quickly. And when I think about robots and just thinking also about the previous talks, I just don't believe that we can prepare a robot for all of these task variation a priori. We have to enable the robot to learn these skills on the fly, basically. So even if our simulators become really great, we won't be able to pre-train a robot for all of these skills in simulation. We have to enable the, sorry. Okay, thank you. We have to be able to, we have to enable the robot to train these skills on the fly, basically. And so that's where I'm coming from. And the thing is, I have this robot in mind that can do this autonomously. So with a user at home that is not a robot expert, right? There is no expert at home that can tune reward functions or set the learning rates or give the perfect demonstration by guiding the robot. We want to have a normal user at home and still enable, enable that user to teach new skills, for example, or for the robot to learn things autonomously. The underlying framework that I use throughout this talk is a model-based framework. So I assume that the robot is able to learn a model of how its actions and in the current state will change the next state. And the next state can capture the robot itself, but also the environment. Although mostly in this talk, I will be focusing on the next state being only the robot state, the visual robot state, or the object state that the robot is manipulating. Okay, in my ideal world, this is a task-independent model. I don't know that this is feasible, but that's often how I start thinking about problems. And then when you have such a model, then all you really need is a cost function that describes the task. And then you can use that model to optimize the cost function by predicting action sequences or policies that optimize this cost and then executing the action sequence. And and then again, in my world, so this cost function is task dependent. It actually captures the task. And I would love for robots to be able to learn these cost functions from things like visual demonstrations. Yeah, so this is kind of the high level framework I tend to think about. And now in this talk, I will first talk about how we can actually learn these cost functions from visual demonstrations. And then I will talk a little bit about the challenges of learning this visual dynamics model, because this model needs to predict visual next states for it to be useful in this cost function learning framework. Okay, so let me start with this side. So learning from visual demonstration is something that a lot of people look at. There's a ton of motivation. We as babies do this ourselves. Okay, I hope you can't hear much. And So that's what we're aiming to do here. Okay, 1 second, sorry. Sorry. No. Now. No, just give me 15 minutes. Okay. Okay, so we want to learn this cost function from visual demonstrations. As you can already see in this video here, what we end up doing is extracting some latent visual state on the object, and I'll talk about how we learn this. And that's the space that the cost function is learned in. And then at test time, we want to use this cost function for a new task to optimize, to basically repeat the task, but for various task variations. And I'll start talking about first how, given a cost function, we optimize a policy such that it can execute the task that is described by the cost function. And then I'll talk about the cost function learning part. Okay, so the framework we're using is a visual MPC framework. We have an initial position given of the robot, and we extract keypoint state. We measure also the joint state. We have a keypoint dynamics model, like a visual dynamics model that predicts, given the current keypoints, the current joint state, and some action U, what the next joint state, predicted joint state and predicted keypoints would be. So this is something we have to learn. This is the model I was talking about before. And then we unroll this over time horizon T. So we have T actions U. We get our final predicted joint state and key points, and then we measure the cost between the goal key points and the predicted key points. Alternatively, the cost can also take in all the T time steps. That's not super critical right now, but yeah. And then we optimize these actions U via gradient descent right now. And these goal key points, they're extracted from, let's say, the goal position here where I place the object. I use our key point extractor to extract the goal key points, and then that's our target basically. So that's the cost function gets this as a variable, so to say, and then the predicted key points, and it measures the cost between the predicted and the final goal key points. So that's kind of the visual MPC pipeline that we're using. Just to give you an idea of how we train the individual pieces. For the key point detector, the very first, like the initial data that we collect is just the robot arm moving to random configurations and rotating the object. And then we use a key point learning framework to extract key points on that data, and then we keep it fixed. The dynamics model, I'll talk about in a minute how we get the data, but for now, this is just the joint state we assume is being just integrated forward. So we assume we can, the actions U, we can achieve them, their desired velocities of the joints. And then the key point prediction, so the latent state prediction is modeled by a neural network. Oh, this is it, basically. So this is just a forward integration of the joint state, and this is the prediction of the next key point state. Yeah, so those were the kind of two components that were learned in the visual MPC pipeline. Once those are learned, we can extract now cost functions from visual demonstrations. The way we did this in this paper is to frame this as a bilevel optimization framework. So for the people, I'm not sure how familiar you are with model-based inverse reinforcement learning, but inverse reinforcement learning is the problem of learning reward function or cost functions. And there are various formulations out there, and we recently proposed to frame model-based inverse reinforcement learning as a bilevel optimization framework, where the upper level tries to minimize the visual latent trajectory of the demonstration. So we take the demonstration, extract the latent trajectory, and the predicted latent trajectory. And if you keep in mind how we create these predictions, then you know this is actually a function of the cost or reward function, because we're predicting by minimizing this cost or reward. And so basically the lower level actually now optimizes this reward function to such that so basically such that this distance is minimized. Yeah, I'm happy to talk more about this, but yeah. So we have this bilevel optimization framework to learn the reward function. And then this is one of the results. This is me placing the object on the table. And one of the things that I want you to watch out for is that how I first move it over the shelf and then down. These are different cost functions we're testing, and most notably, so these are all learned cost functions, while this is a default distance, just a mean squared error loss between the goal key points and the current key points. And when you minimize that, you start to like collide with the shelf, because you're not learning that you first have to go over the shelf and then down. And all of these cost function learns some sort of behavior like that from the demonstration, because that's what I'm showing. And really the cost function that have some form of time dependency work the best here, because yeah, I didn't go into the details of this, but that's depending on the how you parameterize the cost function basically. Okay, let me quickly go to now what this part. So I told you I will talk a little bit about how we train this predictive model later, like I tell you later about it. And the thing here is that this is actually one of the most challenging parts of this pipeline, learning a predictive model that works well enough such that you can predict over a longer time horizon. So the consequences of the robot's action basically. And what we ended up doing for this work that I just presented was that we actually needed to design expert controllers that can like cover the area that we needed to get data from. Then we collected the data. So we already had to solve the placing task in a sense by designing an expert controller, get the data, and then learn the model. And then, you know, we pretended we don't have the expert controller and we actually want to learn this controller. And that's of course annoying, because my goal is to autonomously. So when a robot is in your home, you don't first have to design an expert controller to get the right data, such that you then can learn the cost function, or such that the robot can then learn the cost function autonomously. So I've been starting to think a lot about what can we do here in this model, like can we infuse some structure? So before I go into that, I want to just kind of outline a little bit more why this is so hard. So first of all, we're predicting 2D image key points. So the dynamics model, this visual dynamics model is learned in 2D space, but the control actually happens in 3D workspace. So that's one of the issues. The key points, they don't really fall on the object and are not forced to consistently track the same part of the object. So this specific key point method that we used, it works fairly well to find key points of moving objects in a sequence of images, but it doesn't necessarily track the key point robustly on the same piece of the object. And then there is just a general problem of using neural network models to model such visual dynamics, because these unstructured models, they still suffer from poor generalization capabilities. So that's a very big challenge. Yeah. And what we have been doing recently is to, I'll shift gears a little bit, but I'll bring it back in a moment, I promise. We have been developing analytical robot models. So here you see a robot model with 7 links, and for each link we created a PyTorch module in a way, and implemented differentiable and learnable kinematics. That's kind of what's relevant for this talk right now. And that means that we have a model that we can add some additional link to, like an object link. And we can also estimate these parameters from that object that we're attaching now to the robot. And that's what we end up doing. So I'll show you in a moment. This work is that we call this learning extended body schema from visual key points. So we present an approach that learns first the visual key points, as I've just been talking about right now, but we use multimodal information now to improve the prediction of the key points. And then we show how we can extend such a kinematic model that I just showed you to include an object in the manipulator's hand, and how we can estimate this from the visual key points. So this is kind of the key point pipeline or algorithm that we've been using. I'm not sure I added the citation, I forgot the citation. This is a paper from Mindera et al., where initially the initial results I showed you, this is just using this out of the box. It's an autoencoder framework with the key points being the bottleneck. So everything has to go through key point, this key point representation, and then it needs to be, the images need to be reconstructed from there. As I've said, there's some challenges with this, and I'm going to start. So first, the joint state measurements. We might not be perfect, but we do have them. So can we use them? And because we have this this kinematic model, can we use this kinematic model to create a kinematic feature map in the visual space? So here we also assume that we have calibration of our camera, basically. And that allows us to predict the end effector position in image space. And we just create a Gaussian around this. And then we fuse this with the visual feature map that our ResNet encodes, basically. So it's fairly simple. It's just an addition. The benefit of using such some sort of simple approach is that this addition means that we can only leave proprioception out when we don't need it or don't have it. We can map basically as an additional feature map. And then we first evaluate this. So the initial key point detector that we showed is in blue. And now our new multimodal key point detector is in orange. And what we're measuring here is the distance. So we know that because we're doing this in simulation, this experiment, and to be precise, we're doing this in the habitat simulator that was just presented as well. We also know the ground truth location of the object, so we can actually measure the distance of the key points to the object, and you can see that the multimodal detector starts predicting key points that are closer to the object than the initial key point detector. So, and that's what we wanted, right? Because we really want the key points to fall on the object as much as possible. And then we actually thought about what we thought was interesting about this multimodal key point detector is that we don't need proprioception. And so we had this question of how much proprioception do we need at training time to learn, to improve key point prediction. And what you see here is if we use only the visual data, and no proprioception, this is kind of the performance that you get. So this is again the distance of the predicted key points to the ground truth object location. And as more of the data in the data set can use proprioceptive states, you actually get better key point predictions, but it is leveling out here at some point, right? So you don't actually need to give all the data proprioceptive state measurements. And what that tells me is just that there is a lot of work that we could do to understand how the robot can learn from active data where it measures its own joint state, but also from passive data where it watches other people or videos and mix that data basically to learn representations. And that's just this is a video of what it looks like. This is the initial key point from Mindera and all. And you see here the 2 key points don't fall on the object. And this is our representation. Okay, and then finally, I said I wanted to replace the key point, the dynamics model, the visual dynamics model with the structured model. And we do this with this differentiable and learnable chain. We attach representation. We know that we're predicting 3 key points, so we're given 3 virtual links that we don't know the values of, but we are learning these values now from the visual key points. This can be framed as a regression problem. And then once we do that, we can now actually use this representation, this virtual kinematic chain to perform the control task. And one thing I want to kind of shout out is that I think a lot of work is being done currently on like trying to improve these unstructured neural networks, like the long-term prediction. So here you see the prediction performance of the various neural network variants and ours, which is in orange, and the rest is all different neural network variants. These neural network variants also include, for example, depth information, just to make sure it's not the issue of 2D versus 3D prediction that is causing the difference. But what you see is all of these neural network representations, at some point, they just explode in error, if, you know, as you're predicting forward over a longer time horizon. While with a very structured model like this, you get near perfect, I mean, it's not perfect, but very good prediction performance. And you can see the result of this on the actual placing task, that the placing with the structured model performs much better than you know, any of the representation. I think all the collaborators that were involved for pieces work. Thank you for listening.
Thank you, Franziska. We can have some questions from the audience. You can raise your hand or type in the chat box. I can start with one. I'm curious, how do you detect these key points, and how do you choose the key points?
So the key points are trained via the key point detector, that the different variations that I talked about. And so we just have to collect data and train the model. Yeah.
So like a visual model for key point detection.
Yeah, exactly.
I see.
Yeah.
Questions from the audience? So maybe last one from me. You talk about this differentiable kinematics, right? Do you use a neural network to compute the kinematics?
So this differentiable kinematics is a analytical like implementation of the kinematics in PyTorch language, right? So it's almost like you know, you can think of it as a neural network, but a highly structured parameterized neural network. Yeah.
I see. We got one question from Sansos. How do you select the number of key points? do they have semantic meaning?
Played with very Keypoint paper, we also showed these results, and we basically just ended up picking the ones that work the best. So we don't have a good method right now to know a priori how many key points we need. In our current work, they don't have semantic meaning yet, but this is something I'd love to explore, how we can learn key points that have a meaning on the object, right? When you're pouring a bottle, you would care a lot about maybe the top of the bottle, and you would like to have a key point that captures the top of the of that bottle. So yeah, but then of course it depends on the task that you're trying to do. When you're trying to place the bottle, the bottom matters more. So that's a very interesting research direction, but we're not addressing this in this work.
Thanks